Our next speaker is Spencer Weart. Dr. Weart served as the director of the Center for History of Physics at the American Institute of Physics from 1974 to 2009, now retired. And he taught history of science courses at Johns Hopkins, the New School Lang College, and Princeton University, and served as the treasurer and council member on the History of Science Society. His talk is entitled The Rise of Interdisciplinary Climate Research.
So I gather this colloquium is all about variety, so we just heard a talk that was all about the future, so now we'll hear a talk that's all about the past. You know, I like to say that scientists are people who are mainly concerned with changing the future, and historians are people who are mainly concerned with changing the past. So I'll try to at least give you a view of the past now. So we're going to start out by talking about the old climatology. Going back to the middle of the 20th century, the kind of people who called themselves climatologists were mostly drudges. Study of climate was a scientific backwater. The climatologists compiled statistics about weather, average temperatures, extremes of rainfall. They put aside the planet as a whole and concentrated on regional features. The people who wanted climate information were people like farmers and engineers who were building dams or bridges. And so they were concerned with the possibilities of a decade-long drought or of some extraordinary 100-year flood. So the job of the climatologist was to remove the uncertainties with statistics. And this was a static view of climate. It had nothing to do with climate change. In fact, the idea that the climate as a whole could change was entirely opposed to the idea of describing what was called a normal climate of a region. Quite typical was the situation at the U.S. Weather Bureau. In 1953, an advisory group reported that in the Bureau, climatology was exclusively a data collection and tabulation business. In fact, the entire Weather Bureau, as a scientist later remarked, was the stuffiest outfit you've ever seen, deadly, deadly dull. And climatology, as one practitioner complained, climatology was the dullest branch of meteorology. Not much money, not much administrative attention was going to be given to this kind of work, and the intellectual prospects were hardly enticing. At most, if a worker had a research plan, his aim was just to find a better way to synthesize the piles of data. Here's some of the punch card storage that had overflowed the storage rooms, that had overflowed the corridors. The punch cards were now being stored in the entrance hall, and in fact, they were worried that the building was going to collapse under the weight of the punch cards. So a climatologist was somebody who described climate. And these climatologist products, I should say, were highly appreciated by their customers, and these kind of studies continue to this day. It was useful stuff. And in fact, this tedious and painstaking style of work did turn out to be indispensable for the studies of climate change, so I don't undervalue it. However, as an expert remarked, in the study of climates, the scientific principles involved are barely mentioned. Whether they are right or wrong does not seem to be of any moment because they are never used to calculate anything. When climatologists tried to go beyond statistics to explanations, they would explain the temperature and precipitation of a region in terms of geographical zones. The sunlight at that particular latitude may be adding in some of the prevailing winds as modified by mountain ranges or ocean currents, that kind of a thing. The explanations were chiefly qualitative, with more hand-waving rather than equations. This was very close to the field that was called physical geography, as a matter of classifying regions. Less interest in the causes than in the consequences. Of great interest to imperialists and people like that wanting to know what kind of crops you could grow in a particular area. So at the first half of the 20th century, if you looked at somebody who called himself a climatologist, you would probably find him in the university geography department, if you found him in a university at all. And this, again, was an essentially static exercise. Physics itself was useless for telling farmers what crops they needed to grow. Most textbooks of climatology, if you go back and look in the old textbooks, you'll find that they were stuck to listing descriptions. They were descriptive, telling about what the normal climate was in each geographical area. And one scientist complained that textbook authors themselves know little and care less about physical science. Well, climatology could hardly be scientific when meteorology itself was not a science so much as an art. Climatologists would try to predict a season by looking at what was happening in the past. There was something similar going on in meteorologists. You tried to predict the next day's weather. One way to do it was to look at a weather map. You go through a whole atlas of weather maps from the past to try to find one that looked similar and then see what had happened. More often, the forecaster just looked at the current situation and he drew on his experience with the combination of some simple rules of thumb and just personal intuition. In fact, a canny amateur with no academic credentials could often predict the weather better than a PhD meteorologist. Indeed, most of the so-called professionals in the U.S. Weather Bureau did not have even a college degree. So there were a few professors and a few pioneering institutes, mostly in Europe, geophysical institutes in Germany and so on. But aside from these people, meteorology was scarcely seen as a field of science at all. As one meteorologist, an academic meteorologist, complained to another in 1950, meteorology is still suffering from the trade school blues. Since the 19th century, the forecasters and the statistical climatologists had gone separate ways. Neither group had much to do with the few professional academics trained in physics who from time to time did try to analyze weather patterns with equations. As one scientist recalled, in the 1940s, academic meteorologists would sometimes go out of their way to disclaim any connection with forecasting, an activity of dubious scientific standing. So here was the situation. There was weather forecasting, there was statistical climatology, and there was a few people doing theoretical meteorology based on physics, and these people had very little overlap with one another. Now, since climate did average over the random daily fluctuations of weather, there were some people who did hope to make more of an overlap between climatology and theoretical investigation, scientific investigation. They tried to understand climate change, because after all, they did know that climate changed, so there were the ice ages. So over the periods of, let's say, tens of thousands of years, you knew climate could change. So they tried to understand this kind of change. And also, weren't there regular, within these large-scale changes, weren't there climate cycles? So they would carry out grinding numerical studies in hopes of pinning down recurrences and perhaps predicting them. Analysis of large sets of data did turn up various plausible cycles, mostly correlated with the sunspot cycles. And you could carry it through 10 cycles and find there was a correlation, but then of course when you made a prediction, the next cycle invariably turned out to cancel out your prediction. The correlations invariably turned out to be spurious, which further lowered the poor reputation of scientific climate studies. It was all a matter of speculation. Was it changes on the sun that made for ice ages over these cycles that people purported to see? Was it changes in volcanic emissions? Was it shifts in the Earth's orbit, to take a particularly outre possibility? Was it shifts in the ocean currents? There were all these kind of elaborate mechanisms. Each person had its own particular theory for what made for climate changes. The respected climatologist, historical climatologist, Hubert Lamb, said that I, for one, must confess to having been bewildered and left quite pessimistic by some discussions of climatic variation. In fact, the very concept of theory became suspect in climate studies. If you said you were working on a theory, people would tend to say, well, good for you. Well, the next phase began with the Second World War, which changed so many things, and we now come to the era of meteorology and geophysics. During the Second World War, meteorology professors trained thousands of meteorologists for the armed services. And this training gave a big boost to the few universities where scientific meteorology was being attempted. And it led to further expansion after the war. Let me just give a couple examples. A young geology student, Reed Bryson, was picked up by the Air Force and shifted from geology because he was trained in weather forecasting for the armed services. After the war, he went ahead and got his PhD in meteorology. He went into the geography department at the University of Wisconsin. He found himself unwelcome there. So he set up a one-man meteorology department. And in 1962, the newly funded National Science Foundation gave him funds to establish what became an important climate research center. We'll see him again later on. Another example was Ed Lorenz. He had intended to be a mathematician, but he too was diverted into meteorology during the war when the Army Air Corps put him to work as a weather forecaster. So Bryson and Lorenz were among the new breed of young Turks, as they called themselves, who broke away from the tradition of climatology as a mere handmaiden to forecasting. Leading the movement was a group at the University of Chicago. In 1942, Carl Gustav Rossby had created a department of meteorology. Now, Rossby was a Swede. He had learned mathematical physics in Stockholm, and then he spent 2 years at Wilhelm Bjerknes's group. Here's Wilhelm and Jakob Bjerknes with their meteorology group in in Bergen, Norway. Of course, it was in Bergen that some of the key concepts of meteorology had been discovered, notably the weather front. They had this improved understanding of weather patterns, and Bjerknes's group came to think in climate not so much in geographical terms, not so much as a matter of latitudes and locations, but in terms of the weather systems that were typical. So a climate was not defined by a place, it was defined by the weather patterns that were there. And if the pattern of weather systems in a region changed, didn't that mean a change of climate? It was a new way of looking at things. It was what one of the people here called a dynamical climatology. That's Tor Bergeron, the person at the far left here, spoke for the first time of dynamical climatology. So here's Rossby. He came after a stint in this group to the United States in 1925 to work at the Weather Bureau. He soon left the somnolent bureau in disgust. In 1928, he created the nation's first professional meteorology department at MIT. And after he moved to Chicago in 1942, he did more. There was ample wartime support for training meteorologists. Many hundreds of them moved through Chicago. And this support continued after the war because of the Cold War and the expanding economy, particularly the growth of civil aviation, made for a rapid expansion in the demand for trained meteorologists. So the Chicago group flourished. And it was the first group anywhere to systematically try to develop physical models of climate, including actual physical models. Here's a reproduction of Dave Foltz's experiment where he has a dishpan, he puts on a rotating turntable to simulate the rotating Earth. He heats it around the periphery. He puts some ice in the middle for the North Pole. The periphery is the equator. And he gets something that looks like weather patterns. So this is physics now, or is it meteorology? Well, you see, that's an attempt to bring physics into meteorology. And so there's a new approach, and lots of students went from Chicago to carry out this approach elsewhere. And meteorology began to gain a reputation as a truly scientific discipline, with climatology following in its wake. As Rossby remarked, they were now taking up basic questions, new questions of climate change. For example, how did heat get stored in the oceans? What was the level of carbon dioxide gas in the atmosphere? This is a completely new class of questions. Completely new. Well, somehow I went back. Okay. Well, anyway, the quote was that it was a completely new class of questions. They were looking at the entire planet as a physical system. Now, it helped that the entire area of geophysics, which included most of the fields relevant to climate studies, was becoming stronger and better organized. Now, if we look back at the history of geophysics, at the beginning we see these geophysical institutes, primarily in German universities, which embraced a wide enough range of studies to term themselves geophysical. Already in 1919, an International Union of Geodesy and Geophysics had been formed, with separate sections for the different fields, terrestrial magnetism, oceanography, and so forth. But as one of the founders of the union remarked, it was not so much a union as a confederation. Likewise for the American Geophysical Union, which was also created in 1919, incidentally as an affiliate of the U.S. National Academy of Sciences. There followed a few other national societies and journals, such as the Zeitschrift für Geophysik, and several German universities created formal programs teaching geophysik. However, most individuals who might be called geophysicists did not call themselves such. They did their work within the confines of one or another traditional discipline, such as geology or meteorology. Beginning in the late 1940s, a more significant number of inclusive institutions appeared. More institutions of geophysics were created at American universities and under the Soviet Academy of Sciences. Another big boost came in 1957, 1958 with the International Geophysical Year, which of course pulled together thousands of scientists from many nations to interacting with one another in committees that conducted truly interdisciplinary research projects involving projects that involved a dozen or more geophysics fields. Most of these fields, again, relevant to climatology. The annual meetings of the American Geophysical Union became a rendezvous for diverse fields. For the same purposes, the union began to publish this Journal of Geophysical Research. But I must say, when I looked back through the writings of the 1950s, it seemed to me that for the scattered scientists, still widely scattered, who were concerned at all with climate change, the best meeting place was TELUS, so-called Quarterly Journal of Geophysics that was put up by the Swedish Geophysical Society since 1949. Now, it seems like things were getting together, but in fact, this was an era, oh, there it is. Okay. Well, it seemed like this was an era of getting together, but in fact it was also an era of fragmentation. Because in geophysics, as in all the sciences of the 20th century, expansion raised this risk. Early in the century, so little had been known about any given field of science, especially geophysics, that the best scientists had broad knowledge across many aspects of the subject. For example, here's Harold Sverdrup in the Bjerknes group. Between the two world wars, Sverdrup published research on the circulation of the atmosphere, the circulation of the oceans, glaciers, geomagnetism, and the tides, not to mention the ethology of Siberian tribes. A few decades later, when knowledge had become deeper and techniques had become more esoteric, hardly anyone could do significant research in more than one field. It was getting ever tougher for a scientist to become an expert even in one field, let alone in a second field of knowledge. And few people attempted it. For the diversion of energy, risk your career. In fact, that's what happened to Jack Eddy. He was a solar physicist who did some work on Indian astroarchaeology, and it did not help his career. And in fact, he found himself at loose ends, which only inspired him to go and do work in yet another field, going from solar physics into climate. Here's how he put it. Entering a new field with a degree in another is not unlike Lewis and Clark walking into the camp of the Mandans. You are not one of them. They distrust you. Your degree means nothing. Your name is not recognized. You have to learn it all from scratch, talk to the right people, learn that stuff. In fact, some of the most important discoveries came from people like Eddy, who did spend years in a foreign camp. Eddy, of course, is the person who first pointed out how the Maunder minimum of sunspots was related to the Little Ice Age, and went back to trace through carbon-14 studies and so forth the correlation between gross solar activity and climate. And here's how Eddy put it. I think that many of the greatest discoveries generally come at the boundaries of the disciplines, the terra incognita, where things are not looked at. It's not a place that's hidebound by practice and ritual. Here's another example, Nick Shackleton. He started out by studying physics, which turned out to be essential for laboratory work measuring isotopes. He also studied mathematics, which was necessary later on for his analysis of time series. And then he became part of a research group that analyzed pollen in a university botany department. Of course, the eventual result was landmark work on the timing of the ice ages. But such combinations, however valuable, were becoming very uncommon. There were fewer and fewer people like Shackleton or Eddy or Sverdrup who actually worked in more than one field. And this problem was particularly severe for climate studies because there never had been a community of people working on climate change. There were only individuals with one or other interest who usually would take up a climate problem and study it for a couple of years and then go back and work on other things. And each had its unique area of expertise. I mean, think about, let's say, an astrophysicist who is looking at changes in solar energy, a geochemist who is studying the movements of radioactive carbon, a meteorologist studying the global circulation of the winds. They were not likely to meet at a scientific conference. They were not going to read each other's journals. They probably did not even know of one another's existence. In fact, Eddy was working on the Maunder minimum for quite some time before somebody told him that people had already made connections between carbon-14 and solar activity. He just hadn't heard about it. As one climate expert remarked, lack of interest has all too often characterized the attitude of physical scientists to the masses of information produced by botanists examining pollen deposits, the data turned out by geologists, glaciologists, entomologists, and others. These types of literature have never been part of their regular diet. I must say it's been my feeling that communication was made even harder because different fields attracted different kinds of people. If you go into the office of a statistical climatologist, you would find these ranges of well-organized shelves and drawers with neat stacks. In later years, they would hold computer printouts, which were the result of long days spent coding data. The climatologist was probably a person like Murray Mitchell, who he had set up his own weather station at his home and meticulously recorded daily wind speed and precipitation year after year. If you go into the office of an oceanographer, you're more likely to find a jumble of curiosities from the shores of the seven seas. You could hear adventure stories like here's Maurice Ewing. He told how he was washed overboard and narrowly escaped drowning. Oceanographers tended to be salty types, accustomed to long voyages far from comforts of homes. You may be aware they're outspoken and sometimes self-centered, a long way away from the statistical climatologists. Now, these differences in personality went along with differences in matters as fundamental as the kinds of data that people acquired and how they acquired them. Meteorologists used mainly standard observations that were made by technicians by the million, going back centuries. And oceanographers usually made their own instruments, made their own measurements with instruments they made themselves. As one oceanographer remarked, meteorology and oceanography are practiced in a very different manner and by two largely non-overlapping groups of people. There are still relatively few meteorologists who have more than a superficial knowledge of the ocean, and vice versa. So this was the fragmentation. And on top of these social and perceptual gaps, there were technical divergencies. The data that one person measured was not the same as the data another person measured. As one expert remarked, the fact that there are so many disciplines involved, for example, meteorology, oceanography, geography, hydrology, geology, glaciology, plant ecology, and vegetation history, to mention only some, has made it impossible to work with common and well-established definitions and methods. Comparison between the results have been hardly possible, and you find cases of collaboration where the first year is spent just agreeing on a common definition of the data and a common understanding of what the data actually represented. So the situation, however much may have been done, still was very much in this kind of thing. There was the feeling of getting together in certain things, but the reality was not there. Now, what drove this was the next phase of things, the confrontation with climate change. The fragmentation was becoming intolerable largely because of observations of the climbing level of carbon dioxide. This is an early phase of the Keeling curve, where you see the annual variation and the steady rise of carbon dioxide in the atmosphere. Also, there were scholarly studies by historians, him and others, extending the climate record into the past and finding things like the Little Ice Age. So it was recognized that climate change, serious climate change, was not something that happened over the time scale of the ice ages, tens of thousands of years, but it was something that could happen, in fact, on a human time scale. So the combination of the recognition of rapid climate change and the observation of the rapid rise of carbon dioxide forced people to pay close attention to things. And then, let's see, no, I'll get back to that in a minute. So it wasn't easy to accept this unhappy fact. As late as 1968, I found a textbook on climatology that said boldly, quote, "The subject of climatic change is not given specific treatment in this textbook." Applied climatologists continued to base their projections of the future on their hordes of old statistics, because after all, what else did they have? So their work was becoming increasingly useful as they got better and better at it. The database grew, methods for understanding it. The old climatology was still flourishing and produced things like these maps of climate zones where you could do your best to grow things. However, during the 1960s, more and more people recognized that these predictions were not reliable. You couldn't rely on past observations. For example, in 1935, the International Meteorological Organization had adopted the years 1901 to 1930 as the, quote, climatic normal period. This was misleading. That 30-year span turned out to have weather that was far from what was normal in the next 30 years and the next 30 years. Indeed, there might be no such thing as a normal climate. Climate was something that changed continually under the impact of physical forces. This new thinking came out most clearly in 1965 symposium in Boulder, Colorado on the causes of climate change. The meeting didn't make a great impression at the time, but in retrospect it was a landmark because it deliberately brought together, this was the first time that it brought together scientists from a whole variety of fields, experts in everything from volcanoes to sunspots. And presiding over the meeting was an oceanographer, Roger Revelle. There were lectures and roundtable discussions, all kinds of spirited debate as rival theories fought one another. Revelle needed all his exceptional leadership skills to keep the meeting on track. The conference featured a burst of new ideas about what kind of physical mechanisms might bring about unexpectedly rapid climate shifts. And this sort of thinking was spreading widely in the 1960s and early 70s. One reason being that in the early 70s there was a series of devastating droughts and other weather disasters that showed that climate was grossly unreliable. There was a spike in food prices, even bigger than the spike that we have just recently seen. And with this kind of alarming news came warnings that the near future might be still worse. people began to predict a drastic cooling or a global warming. Nobody was quite sure which, but it was clear that the human pollution of the atmosphere was very liable to cause large-scale perturbations. So this brought in an active and aggressive view of climate change in relation to humanity, and it called for more aggressive research. As an authority remarked in 1975, the old descriptive climatology, concerned mainly with statistics and verbal interpretation of them, is evolving into a new mathematical or dynamic climatology with predictive capability based on physical mathematical processes rather than extrapolation of statistical measures. It didn't mean that they had predictive capability, but this was what they were now looking for, basing predictions not on, well, it'll be the same as in the past, but on actually figuring things out physically. Now, this required a new kind of research community, one that was more closely linked among the fields, more interdisciplinary. And this was, in fact, happening in all of the earth sciences. It wasn't just a matter of climate science. The traditional observational geologist out there in the field with his high-laced engineering boots had to make room for the investigator who saw rocks mainly as a matter of something in a laboratory or even just something in a set of equations. The old school geologist grumbled about this. He says that people were getting away from the real contact with nature. They were losing the personal confrontation with nature in all its complexity and grandeur. And the same kind of filtering was happening to climate scientists too. But the new breed of scientists became more and more skeptical of the traditional approach. The traditional approach, as I said, in which each scientist had his own favorite theory of climate change. One said it's something that happens in the ice, another says it's the volcanoes, another says it's something that's happening on the sun, the sun's luminosity. It seemed likely that many factors contributed together to influencing climate. It is now generally accepted, oh, here's Lamb again, it is now generally accepted that most climatic changes are to be attributed to a complex of causes. And so you began to have things like this wiring diagram, obviously a feedback system among all kinds of different things. Soil moisture is there in the middle, the ocean fluxes, temperature, absorbed sunlight, solar radiation coming in. Biology isn't in this one yet. This is a very early one, 1974. But it's obviously some kind of a very complex system which is pointing to the necessity of employing computers, in fact, in order to figure all these things out quite clearly beyond any kind of simple analysis. So the shortcomings of the old simple single cause approach were especially visible to people who were trying to craft these computer models of climate. Here's Suki Manabe, of course one of the great pioneers at Princeton. You couldn't construct a plausible model without information about all kinds of things. Manabe recalled, for example, spending many hours in a library looking up things about soils because he needed to know about soil runoff of precipitation. It became painfully clear that scientists in various fields needed to talk with scientists in other fields. And the specialists did begin to interact more closely. They drew on one another's findings, sometimes challenging them, which was perhaps the most useful thing they could do. But it was the requirements of numerical computation more than anything else that forced these isolated communities, the empirical climatologists with their statistics, the weather forecasters with their practical intuition, the academic scientists with their theories and equations, all began to try to find means to communicate with one another. So this was the main theme I want to emphasize in the 1970s and 80s, the changes in meteorology and geophysics that led to better communication. These were in fact typical, again, of a movement that took place in all the scientists. The 1970s brought into prominence what people were beginning to call holistic investigation. It had kind of a hippie 1960s feeling, but nevertheless it was a very strong movement in all this. In biology, for example, there was the movement towards ecology, which again was strongly interdisciplinary, required you to look at the system as a whole and all of its interactions, which was quite timely because scientists were increasingly realizing that biology was yet another feature that interacted with the climate system. Now, some people had always been aware of these interactions, most notably in oceanography. In oceanography, the physical and the biological oceanographers had always interacted with one another, if only because they had to bunk together on their voyages. All of geophysics, however, was becoming to be seen as part of a larger field, what came to be called the earth sciences. Now, in the fields relating specifically to climate, as in the other sciences, textbooks and review articles in ever-growing numbers were summarizing the recent findings of this or that specialty. So you began to get review articles, you began to get textbooks that you could look into. There were conferences that were held after the Boulder Symposium. There were increasingly all sorts of conferences that brought together people, anywhere from a dozen to 100 people, and from different but relevant fields. But most scientists continued to call themselves oceanographers or computer scientists or paleobotanists or whatever. Not many would identify themselves as primarily, what would you call it? You couldn't call yourself a climatologist, so it wasn't clear what you could call themselves. And the typical landmarks for the creation of a discipline, departments at universities, a scientific society named for the discipline, these never came. The key elements for any profession are socialization and employment. For scientists, it usually meant training as a graduate student and employment as a professor. And these remain firmly within the traditional disciplines like meteorology or oceanography, or the umbrella term of earth science or geophysics. There was one landmark for the creation, the recognition and coalescence of a scientific discipline. It was the foundation of a dedicated journal, Climatic Change, by the late, much regretted Steve Schneider as the founder. However, unlike many new journals, this one did not, in fact, launch itself as I am the flagship of a new discipline. Its explicit policy was to publish papers that were mainly interdisciplinary. For example, you might explore the consequences that global warming might have on an ecosystem. Schneider said later that he took up the task, as he said, despite his institute director, because the institute director had warned him that if he pursued interdisciplinary work, it would hurt his career. And in fact, many scientists did believe that solid research could be done only within the strict framework of a traditional discipline. So most scientific papers on climate change continue to be published in journals dedicated to a specific field, like the Meteorologist's Journal of the Atmospheric Sciences, the Paleontologist's Quaternary Research. That's true to some extent still, of course. But key papers were also increasingly welcomed by the two great interdisciplinary scientific journals, Science and Nature, a place where specialists in every field would see them. From one climate article in a year, perhaps, it increased by the late 1980s to almost a climate article every week. So the scientists concerned about climate change recognized that they needed these formal structures for communication and coordination. And there were a lot of failures and false starts as they tried to set up some sort of organizing committees or governmental body. And by the end of the 1970s, in the United States at least, they managed to put together some ambitious programs. Although they still lacked central coordination, they each embraced a variety of fields. In particular, the United States established the National Oceanic and Atmospheric Administration, which, as the name implies, brought together two specialties. They were still bureaucratically somewhat separate, but at least they were together in one institution. Within NASA, the need to design satellites to observe the Earth from space gave a push to a sort of a holistic view. And some worked deliberately to break down the disciplinary boundaries and create what they called Earth system science. The specialists in the different fields with an interest in climate change found themselves increasingly meeting in the various committees and panels, especially within NASA, that reviewed and directed the programs. The process was officially capped in the mid-1980s by the creation of an international geosphere-biosphere program, which again, as the name implies, tried to include everything. In fact, some began to work that there would be too many cooks in the kitchen. Now, for studying a system that features dispersed among many specialties, the solution, of course, is collaboration. This trend was strong in all the sciences because of the increasing complexity of the research problems. Specialists in various fields found themselves sharing the same funding agencies, institutions, sometimes even buildings, as in the floor at MIT that we just heard about. Sessions bringing together different specialists in one another climate topic multiplied, especially the meetings of the American Geophysical Union, which had become very large. Here's the registration and a poster session. So these were places where you could meet people, and increasingly there were all kinds of workshops, entire conferences devoted to one or another interdisciplinary topic, like this one here. Perhaps most important, every scientist was reading Science and Nature, which competed with one another for outstanding papers in all the fields, and also, as we know, published news articles or review articles. But this was happening not only in Science and Nature. You could begin to read about climate studies in the popular press and increasingly on the internet. An especially powerful mechanism for cooperation was the formation of specific projects that addressed particular interdisciplinary topics. And there were many, many of these, and I'll just mention one example. A specialist in computer modeling were trying to model the past climate, got together with paleontologists who were observing the past climate to see whether the models were robust enough to actually produce a good map. This was the Cooperative Holocene Mapping Project. It conceived in the late 1970s at the University of Wisconsin, where Reed Bryson's climate group was established. Bryson had been involved with reconstructing past climates from pollen and the like. And the project expanded through the 1980s. They brought in more and more domestic and foreign collaborators. And some of these people would devote their entire research careers to this one project. It was typical of these kind of projects that all the collaborators would get together in a kind of a giant parliament or an assembly at periodic intervals. And meanwhile, there'd be sort of an executive committee of the leaders would get together in somebody's home and drink and hash out the real problems. So now we're finally to the era of cooperation, integration. These kind of projects with multiple contributors were in fact becoming common in all of the sciences. And of the papers on climate change, I've looked through a couple of thousand papers on climate change, and I've done some statistics on them. Of the papers written before 1940, nearly all were published under a single name. There were only a few that were the work of two authors. But as time goes on, you begin to see two authors, three authors. Of papers written in the 1980s, fewer than half had one author, and many of the rest had more than two. And a paper listing, for example, 7 authors is no longer extraordinary. Here's one of the papers of the COMAP project. It has 33 authors representing a number of different countries, in fact. This trend continued through the 1990s, and it began to become rare to find any paper that had only a single author. In addition to these kinds of collaborative projects, the internet helped bring people closer together, both on projects and the people who were not on the same project. After all, email made it much easier to argue out ideas and exchange data, and you could have as many people listening into the conversation as you liked. And a few climate scientists went on to maintain blogs, notably realclimate.org, which encouraged a still more universal climate interchange on climate topics. Still, the most important mechanism was the one that sustained scientific communities for many years in the past. You went to meetings and you talked with people. As one scientist, and this is Gavin Schmidt from Real Climate, described this system, most successful scientists develop networks of trusted sources, people you know and get along with, but who are specialists in different areas and who you can just call up and ask for the bottom line. They can point you directly to the key papers related to your question or give you the unofficial buzz about some new high-profile paper. Climate scientists increasingly realized that they needed more than anything else because the complexity had increased. Here's a wiring diagram from the 1980s. For some reason, soils are also at the center of this one. I'm not quite sure why, but it includes all kinds of biology as well as ocean dynamics, marine geochemistry, terrestrial ecosystems, as well as cloud processes and so forth and so forth. So this is the kind of wiring diagram and the kind of very large number of specialties that you needed for a computer model. Now, if you ask for a wiring diagram of the scientific societies that corresponded to this, you would get this kind of a thing. The scientific societies were in no sense coordinated in the same way, but this was no longer acceptable because climate scientists had become increasingly important for policy. It had become a public policy issue. And so the world's governments demanded a formal advisory procedure. And of course, as you know, the result was the Intergovernmental Panel on Climate Change, which was, of course, not really a single panel. It's a nexus of uncounted international workshops, exchanges of draft reports, arguments among individuals, God knows how many email messages involved. In some fields, the IPCC process became the central locus, the focus of arguments and conclusions, and this went farthest for the people who used supercomputers. The modeling efforts increasingly focused on cooperative projects to produce results for the IPCC's regular assessments. The whole cycle of supercomputing with climate models became tied to the IPCC reports. When climate modelers studied the details of each factor that went into their calculations, of course, and when they sought data to validate their models, they had to interact with every specialty that had something to say about climate change. So finally we have this kind of interaction, which was largely centered on the GCM. So GCM originally stood for the meteorologist's general circulation model, general circulation of the atmosphere model. Later on, it was renamed the global climate model. And of course, now they've changed the acronym and it's become the Earth System model that we just were hearing about. This work was oriented around the series of IPCC reports, and every computer group, and also the people who are working on other topics, not computer models, but paleoclimate or whatever else, they felt an intense pressure to come up with answers, and they partly because it was demanded by the world's governments and partly because of our own rising anxieties about future climate. So there were countless grueling exchanges of ideas and data, and the experts in each field hammered out agreements over the sort of lowest common denominator of what they could say for sure and what the uncertainties were. This is something entirely unprecedented in the history of science. I would say entirely unprecedented in the history of any kind of human enterprise, this sort of coming together to come up with the best answers that we could. It was, in fact, a great engine of interdisciplinary research. In the world of science, it was a social mechanism whose size, scope, complexity, efficiency, as well as its importance for future policy, were something entirely new, and I think one of the most positive developments that we have seen in our lifetimes. Okay, thank you.